Right, in this video, we're going to be learning about polarity. It's a pretty important concept in biology as well as chemistry. It has a lot of sort of applications in how things work in the real world. Couple questions to review from last time, electronegativity, and then ranking some things in terms of how electronegative they are. So take a minute, you can pause the video and try to answer those. So electronegativity is really just a measure of how strongly a certain atom attracts electrons. Some just pull in electrons more strongly than others. And our electronegativity, if this was like a periodic table here, kind of rough periodic table, it increases in this direction up the periodic table, except the last column, let's say this is the noble gases, are not electronegative because they already have all the electrons they need, so that one would have zero electronegativity. Our most electronegative element is fluorine, so that's going to be first. Next we would have oxygen right next to fluorine, and then nitrogen, then carbon, and then phosphorus and hydrogen are pretty close to each other. They're both not very electronegative. So when we have two different kinds of atoms bonded together, like in this picture we have a hydrogen bonded to a chlorine. In a covalent bond, we know that electrons are being shared, right? If we were to do the Lewis dots, it would be kind of like that, with these two electrons being shared between the hydrogen and the chlorine. However, due to differences in electronegativity, those electrons are not being shared evenly between the hydrogen and the chlorine. It's kind of like if you were sharing something with your younger sibling when you were a kid, like maybe you got the toy, 90% of the time, and you let your little sibling have it 10% of the time. It's not an even 50-50 sharing. One of them is getting the electrons closer to it or more than the other. So in the example of a bond between hydrogen and chlorine, chlorine, being clear over on the right side of the periodic table, is much more electronegative than hydrogen. Therefore, chlorine will have those electrons more than hydrogen will. It's an uneven sort of sharing, with chlorine getting the electrons more. So take a minute and think, what does that mean about the charge of chlorine? Well, it means that since electrons are negatively charged, if chlorine has the electrons more, chlorine becomes kind of negative. And if hydrogen has the electrons less, hydrogen ends up becoming kind of positive. So it's not like a full negative charge or a full positive charge like an ion that have like a -1 charge. It might be more like a -0.8 or something like that. We call that a partial negative charge. And so chlorine becomes partial negative and hydrogen becomes partial positive. So if a bond is like this, where the electrons are being shared unevenly, we call that polar, because there's a negative side and a positive side, just like the poles on a magnet. It really is almost kind of like a little magnet. So we can have a bond that is polar, which is really anytime you have a bond between two different atoms, you will have a bond that is polar. But we're concerned about if we have a molecule that is polar. So in a polar molecule, we have one side of the molecule that's kind of positive and the other side of the molecule that's kind of negative, again, because of these uneven sharing of electrons. Now, if the electrons are spread evenly on all sides, if we don't have a negative side and a positive side, we would call that a nonpolar molecule. So this one, HCl, we would call a polar molecule because the hydrogen side is kind of positive and the chlorine side is kind of negative. This little symbol here just means partial. So if I write this, that means it's partially positive. So again, it doesn't fully not have the electrons, but it has less of them, so it's kind of positive. So here are two examples of polar molecules. So take a second, you can pause the video. Which is the negative side of these molecules and which is the positive side? So in order to answer that question, we have to consider which part is more electronegative. So again, on the periodic table, more towards this part of the periodic table. So in this molecule, which is water, oxygen is more electronegative than hydrogen. Therefore, the side of the molecule with the oxygen is going to attract more electrons, and it's going to be partially negative. And the side of the molecule with the hydrogens is going to attract less electrons, and it's going to be partially positive. So you don't want to label each hydrogen as partially positive. We're more looking at the sides of the molecule. Like this is, over here is the negative side, and over here is the positive side. In this second molecule, fluorine is the most electronegative atom there is. So the side with the fluorine is going to be the negative side, and the side with all the hydrogens is going to be the positive side. I don't need to label the carbon. Again, I'm just labeling two different sides of the molecule. Negative side, positive side. So what about nonpolar molecules? Well, generally, if you have a symmetrical molecule, meaning it's the same on every side, you could turn it around and around in your hand and it would still look the same on all sides. If we have a symmetrical molecule, then generally we have a nonpolar molecule. So these in this picture are all nonpolar. If you look at this one, we've got a carbon in the middle and then we've got fluorines all the way around. This is that sort of tetrahedral shape, right, where we've got one fluorine that's kind of coming out at us, and we've got one fluorine that's even with the carbon, and we've got one that's sort of going back. So its three-dimensional shape is symmetrical all the way around, and it's fluorines all the way around. So all of those fluorines are pulling on the electrons, but they're all pulling evenly on the electrons. So it's like a tug of war where both sides are evenly matched. The electrons don't move because it's an even tug of war on all sides. So this becomes nonpolar. Same with this one. We've got chlorines all the way around. They're all pulling evenly hard on the electrons, and so the electrons just don't move. And the same with this one. Fluorines all the way around in sort of this is the flat triangle shape, all pulling. If you imagine, these are all pulling like a tug of war, but they're all pulling equally hard. The middle doesn't move, the electrons don't move. So these are all nonpolar molecules. Now, there's a reason we did this after we learned about shape. The shape of the molecule does matter in determining its polarity. Like if you look at this drawing, this Lewis dot structure, this is water again. And if water was shaped like this, like if it was a straight line like this, we would say that this was a nonpolar molecule. It's kind of the same on both sides, like they would be pulling evenly. But water isn't actually shaped like this, right? Because these pairs of electrons will repel the hydrogens. They'll push the hydrogens down and make it like this. These electrons repel other electrons, and these bonds are made of electrons. So these electrons essentially push away those bonds, and we get this bent shape for water instead of this straight line shape. And now with this bent shape, we do have two different sides. It's not a symmetrical molecule anymore. We have the top and we have the bottom. The top has an oxygen and the bottom has hydrogens. So the oxygen side is negative and the hydrogen side is positive. And this is very important for water because it gives water a lot of the properties that it has that helps it to be so important for life. Right, so here are some practice questions now. You should pause the video again and try to decide, are these molecules, each one, polar or non-polar? And if it is polar, where's the negative side? Where's the positive side? I'll go through the answers now. This one, the first one on the left, this is polar because we clearly have two different sides. We have the side with the carbon and we have the side with the oxygen. Carbon is less electronegative and oxygen is more electronegative. So oxygen side is going to be the negative side and carbon side is going to be the positive side. This molecule is non-polar. It's a flat triangle and all of those chlorines are going to pull evenly on the electrons. So one side's not more negative than another side. It's non-polar, evenly matched tug of war. This molecule is polar because this one is shaped kind of like a pyramid where we have a top, which is where the nitrogen is, and we have the bottom, which is where the hydrogens are. And that's again because these lone pair of electrons are pushing down those hydrogens and pushing them away. Nitrogen is more electronegative than hydrogen, so the nitrogen side is going to be the negative side, and the hydrogen side, the bottom, is going to be the positive side. One important effect of the polarity of molecules is dissolving or mixing. Generally, we say like dissolves like, where polar things can dissolve other polar things and non-polar things can dissolve other non-polar things. So, for example, we know that water is polar. An example of something that is not polar would be oil, like fats or vegetable oils. And you should know that water and oil don't mix. They're just going to kind of separate out into two layers. You can't dissolve oil in water. And then over here we just have a little joke, see if you get it. This bear says, "Help, I'm dissolving." And this one says, "But bears are insoluble." And he says, "That's easy for you to say, you're not polar because this is a polar bear, so it's dissolving in the polar water." But So here's a couple questions to consider. We know that sugar dissolves in water. So do you think that sugar is a polar molecule or a non-polar molecule? And then fats and oils are non-polar. So is soap polar or non-polar? If we think about this, since sugar dissolves in water, sugar is polar. Fats and oils are non-polar, so soap has components that are non-polar. It's really hard to wash like grease or fat with just water. If you try to, scrub a greasy dish and you don't use any soap and you're just using water, that oil is just going to kind of stay on the pan. It's going to cling to it because water is polar and oil is non-polar, so the water can't really dissolve off the oil. However, if you add some soap, the the non-polar parts of the soap are going to help dissolve that oil and fat, and that way you're able to clean your dish. Okay, so that's the end of these notes on polarity.